Hello, everyone, and welcome back to HDL for Digital System Design. So let's dive into the anatomy of a Verilog module. We've already talked about the fact that Verilog can be consumed by different paths, different programs to have different outcomes, right? Simulation versus synthesis. But let's dive into the actual nuts and bolts of a Verilog module itself. So with that, um, the building block, the most fundamental component um, of every Verilog, every HDL ultimately is a module. So we are going to take our designs and they are going to be built up of various modules put together. So easy way to think of a module is think about a chip on a board that has pins. What goes in, what comes out, what happens inside of that, and that would connect to other chips on a board. But now instead of an entire board, take that same thing and think about one device, one design. And so when we design anything, what we think about are the inputs, the outputs, as well as the behavior internally. And so what we can see here is in this particular diagram, imagine that we had what we wanted to have was a LED driver, and that what we wanted to control this driver was a switch, a clock, and a reset. Well, we define all those as inputs. We're using a nomenclature here where inputs are labeled I underscore, and outputs on this particular one, two outputs, perhaps an LED and a busy signal. And then internally, what we want is to assign the output LED equal to the input switch. And that's it. That is what we want to have happen. So something that is likely to come up here is you might be thinking of input and output like function parameters, like, data will flow in through input when you call the module. Well, that's not exactly how this works. In a module, we're talking about physical pins, right? So when you say input, that is literally a wire. We have a wire connecting this input to our um, to our design, and these are real wires. Outputs are things that are being driven by the logic. So you can imagine that the input pins are being pulled, meaning that they're getting a voltage from some source. And on the output side, our design is driving values to to these ports. So there's no function call. The module is always working. It is always there. So there's no yeah, it is always active. So it means that there's no return value, right? Every value that a module produces always comes out of the output port. If you have multiple outputs, I will say that that is pretty much the norm. It is usually the case that modules have more than one output. So here's that template again, where we start off with essentially defining what the module is called, the inputs and outputs, the behavior, and then we are going to close that module off. So first up, the module keyword. So the way that it works, since it's the foundation to all that we're doing, module followed by the name of your module that you'd like to have. Next come up the input ports. So those are all the signals that you have coming into your space, followed by the output ports, all the signals going out. Then you need a semicolon after the closing parentheses for this. So this semicolon right here is pretty important. After that, what is the behavior of this module? How does it work? So right now, this module just assigns the output of LED1 to whatever the input switch 1 value is, right? And It is literally wiring it up. So you can think of this as there is a wire that connects this switch to this LED, right? It is not like it's transferring, it is a physical connection between those two. And then finally, end module just defines the end of the module. Note that there's no semicolon at the end here. Okay, depending on what sources you're looking at, you're going to find some different representations here. We're going to follow the ANSI modern day port style definition versus the legacy version. So left-hand side is what we're going to do, where you define your module, open parenthesis, input, wire, and then basically this particular case has sizes, but that doesn't really matter. But here are all of our inputs followed by outputs, closing parenthesis, semicolon, assignment statement. The legacy version of this would have been to define basically your inputs and outputs at the top in basically just a list format here, and then afterwards define the inputs and outputs, right? So for us in this class, we're going to follow essentially the ANSI style on the left. It declares everything, the direction and type in one place. In general, I find that this leads to less code in general, right? You're not being repetitive, fewer bugs, and it's a lot easier to read. For this course, again, we're going to use the ANSI style exclusively. All right, some naming conventions. Again, these are naming conventions. Again, we're using in this course. Depending on a company that you go to, you may or may not see these. So prefixes. When you see I underscore, it's going to be an input port. When you see O underscore, it's going to be an output port. When you see a W underscore, consider that an internal wire. And when you see a R underscore, consider that to be a register. And that'll be something that is assigned usually at an always block, but we'll talk about that over the course this semester. So pretty self-explanatory. Input and output, I and O, W for internal wires. Again, it'll help you keep track of things that way, and registers for things that will occur when we talk about sequential logic. Okay, this is a course convention. Again, this is not necessarily a requirement of language. I'm doing this, you should do it so that you can always look at a signal and know if it's an input, output, register, or wire just on quick first glance. Okay, so let's build a module from scratch. Now, the code for this exists in a handful of different places, but we will talk about that here in a second. So let me switch over to a different view for you, and we will hopefully get to see that. Yeah, so what we have here is the just VS Code editor. And what I've done is I've cloned our repository for this class. So you'll see essentially that exists here. So you'll notice that we are in HDL for DSD on the left-hand side. That is also where we're at. There are multiple directories in here. There are labs and lecture examples. The lecture examples try to contain, I'll say, the bare minimum amount of code, may or may not have test benches surrounding them or anything like that. But it's again, just so that you can see complete code. And so right now what I have up is essentially the example for the LED driver that we were just talking about, where we have essentially the module, the input, and the output all named as expected, followed by what is happening, the assignment and end module. Now, this code is not going to be able to just work just directly in simulation. We don't have a test bench here. And so I will move over and show you where this is also located, and that is located within the labs to some extent. It's a little bit different, but in the labs, example one, which is where you should start, what you'll see is there's an example that is doesn't have an input, but it has an output. And that is definitely a space that we could go. I'm going to go one step further, and I'm going to look at example two, which is buttons to LEDs. All right, so example two within the lab section area is right here, example 2, buttons to LEDs. If we go also the terminal, before I get too far, we're using NICs in our space. If I were to try to type in iVerilog right now, probably won't work. Yeah, command not found. We're using NICs. The instructions are in the repo on how to get set up on that. Once you have cloned your repository, as long as you've already pre-installed NICs, you should be able to, the very top level, so you'll notice here there's a flake.nix file, you should be able to type nix develop, and you'll need to do this the first time you enter this repository, and anytime you are coming back after closing things down, you'll need to do this again. If I type iVerilog again, or if I just scroll up, you'll notice that running nix develop loads in all the tools that we need for our session, including iVerilog. And I'm going to just type it in here to show you that iVerilog now exists in this environment that a few moments ago it didn't. Okay, just make sure you do that. So from here, I'm going to change directories. I'm going to follow along to where we are also. We are in the lab area. Example, let's see, we're in week 1, day 1. And the example, actually, let's just go to week 1, day 1. Inside of this particular area, right, inside of week 1, day 1, you'll actually find a make file, right? So right here is a make file. There's a handful of make files. So there's a make file. We can take a look at it real quick. You'll see make file week 1, day 1, dispatcher. What this does is it actually creates some helper functions for us to try to get things done. So the way that it works is we should be able to type in make. If we don't type in anything, it will default to some things. But I should be able to do things like make example 1. And let's see if this, see if it will actually do it. It actually is going to go ahead and if you don't type anything else, it actually goes right ahead and it programs the device. Let me switch modes here for a second. Let's show you the device. Okay, so I'm actually in the exact same space as we were before. And what we have here is our device. You'll see that there's one LED on. It is because we just made example 1. And so if we take a look at example 1 here, example 1 starter code, what you'll see here is a module, output wire, right? And we have an assign statement here that sets the output LED to 1. All right. Let's just, for fun, change this to 0. And I saved it. And let's rerun. We don't need to redo the develop here. What we are trying to do, oh, somehow I did exit. I didn't mean to. So if you ever exit, so you got to rerun nix develop here. But we're going to go back to lab, week 1, day 1. We're at the very top level here. If I do a make exe1 and hit enter, what you'll notice is our LED here turned off because all I did here was change this from 0 to 1. Let me do that again. There it is. I'm going to rerun the make example 1 and it should turn on here in a second. Okay, so this is literally also the simplest example we can do, and you should try this as well. But so essentially all I'm doing is I'm changing code in our starter area, and I'm running code at the level 1 above that. So if you look at where I'm at, I'm inside of week 1, day 1, and there's this make file that I'm executing, and I'm able to call and dispatch things in all of these different examples here. Now there's some other fun things we could do. We could do make exe_1 underscore sim. See if there's any simulation. All right, well, what's really cool about that is there is a simulator. And if I open up now the dump VCD that was just created, I will now see a simulated version. Now this is pretty not fun in the sense that all we're doing is we're observing the output here, right? But this output here is always 1. So we should have simulated first, right? But simulated version. And basically we're able to show that. So let me change our code real quick. Let's change this back to a 0. Save it. And let's rerun the simulator. And let's open up this dump file. And we see that it's now 0 at all time instead of 1. So, um, what we've just shown is a pathway to make simulated and programmed versions going 2 different pathways, right? Both to simulate and to synthesize. So I can do again, if I do synth here, I believe synthesis should run through the synthesis process, but doesn't compile or doesn't program. And if I do a make prog, it will synthesize and program. And now we'll get the same behavior, right? LED is off now that I've programmed it. And we also see that that's the case in the simulator. Okay, let's look at one more example here. Let's look at the 2-button solution here. So here is, or multiple buttons in this particular case. So example 2 has buttons to LEDs. And so what we have here is essentially module, name for the module, open parentheses, our inputs, right? I underscore for all these, outputs, O underscore for all of these, and then close parenthesis and a semicolon. Okay, and then we have some assigned statements here where essentially we're going to assign the outputs to the inputs. Something you're probably asking yourself, how does the FPGA know what iSwitch1 is or OLED1 is? Like, how do these names correspond to the things here? Well, it's actually not magic. In this directory, right, in this week1 directory, what you'll notice on the left-hand side here is this go_board PCF. And that is a pin constraint file. This pin constraint file essentially maps different elements, different signal names to different pins on the FPGA. So you'll see here, I'm going to set IO, some name to some specific port. All right. So that is the case for the switches, right? For the LEDs, for the 7-segment display elements, everything here is mapped. You should not have to modify this at all. This pin constraint file is specific to this FPGA and board. Okay. So, but the mapping here, when we are using these signals, right, in our code here, these cannot be arbitrary and random. These have to match the thing we're programming. So if you're like, well, I don't know what variable to use or what name to use for a signal, especially for the inputs and outputs, you can go back to the pin constraint file to see what and how things are named. Now, for this class, you shouldn't have to use the PMOD connector. We will use the UART, and I don't think we will, but if you wanted to use the VGA, those are also listed here as well. Okay, so let's go back. Let's take a look at this particular file that we saw. It's just assignment statements. We also have a test bench. The test benches for most of these are located within the solution space test bench. All right. And so what we'll see here is we have a module. It's called a test bench. There are some elements here that won't synthesize. That's okay. And then we have some buttons where basically we're going to connect our design under test, right? So this is the name of our module, buttons to LED was the name of it, and design under test. And now we make our connections between this test bench and our module. Notice that a lot of these names are the same. That is just convention so that we don't get confused on where things are at. And then we see some code internally to this test bench. Again, we'll talk more about test bench design next week in a couple of videos from here. But what you'll notice is that we have an ability to have an integer, and then do something, right? Initial begin, create a dump file, dump some variables out, have a for loop that's going to iterate, it looks like 0 to 16. That's all the potential combinations for a 4 input space. And what we'll see is we'll have switch 4, 3, 2, and 1, and then this construct that we'll talk about later, and wait 5 seconds. So all this is doing is it is iterating over all the potential combinations for what buttons we could press, and that's it. All right, so that's the test bench. Let's do a make sim. Let's do make example 2 sim. And let's see if that actually worked. We should now, inside of our starter code here, see a dump file, test bench buttons to LED. Let's add all of these. And what do we see? We see the simulated output for what we expect to see. So at 0, I0, all the switches should be 0 and all the LEDs should be 0, right? Because if we've wired them up directly, we expect whatever the buttons are to be whatever is on the outputs. We should see a direct mapping. If it helps you to maybe reorganize these, you can, right? If you want to see like, hey, do these line up? You definitely can do that. And you also can recolor these if you really want to. I'm going to color the backgrounds maybe of ones that are together. Orange is probably a really bad idea. Let's, instead of background color, let's change the signals to the same color. In any case, what you can see here is every time that switch 1 goes high, output LED goes high, right? So it's what we expect to see. It's good that we see it. Can follow that same logic for the other ones. Pretty confident that the simulation is working. So now let's program it. So the path we should take is make example 2. And what we should do is we should do synthesis first, make sure that that passes. And what we get here is we get the answer, or we get this output that does say found and reported 0 problems. So ultimately this did work in terms of being able to map this. We get some output here in terms of statistics. How many wires did it take? Basically how many ports, other things. We scroll up far enough in here, we'll also see potentially the number of LUTs. Now, what's interesting here is we're not doing any logic, right? We aren't really mapping anything. And so how many actual LUTs we use is going to be interesting here because network is combinational. We see our input outputs here, 4, and didn't take very much time. And that's actually about it. So really not much going on here except direct wiring. So not surprising that we don't see right here any LUTs. No LUTs needed. All right, this is a direct wiring from inputs to outputs with no logic in between. So let's now go forward, and instead of synthesizing, let's program this device. So I'm going to program. What you'll notice is the difference between what happened in the prior example and this is that now the last little bit here is we actually ice packed it and programmed. And so in theory, if things work as expected, I should be able to press on a button here. I should be able to hit switch 1 and see LED 1 show up. And there we go, it does. 2 works. 3 also works. And 4 works. We can do now multiple button presses and get those as well. So try it out yourself. Make sure that it is doing what you expect. And there you go. That is essentially the path forward for being able to, at a very high level, program a device. So we did this all from the top level of the lab directory for a week and a specific day. So let me do present working directory for you here. And I can also show you what this looks like in a different terminal window. So real quick here, if you want to see what it looks like, if you weren't to use VS Code or something like that, you'll notice that I am in lab week 1, day 1, right here at the top, right? So we're in the same exact spot, right? And I can do an ls here. and you'll see there's a make file and all of these examples, right? And these are actually the things that you're going to be doing for lab. But I can, if I wanted to see the make file, I could do more make file. And it basically is going to tell us that it's a dispatcher here. And if you don't put in any other options, it's going to use what you do in your starter code, not the solution code. So just know that there are ways to get to the solution code. We'll talk about that later. But for now, you can basically do, if you just do make and an example without anything else, it will build and program your design based off of whatever is in your starter code. Right, so that's kind of dangerous, but it works, and you'll notice that on our device, all the LEDs are off, and the buttons should no longer work. They don't do anything. Um, Also, that part of that is because we've modified our code in the starter space to do no LEDs on. We can quickly go in here. We can do a nano. This is example 1, right? LED on, starter code. And let's look at exe1 here. And you'll notice that it is assigned 0. Let's do that. Perhaps, there you go. Now, a common mistake that I've seen here is if you were to go quickly, you might have left off the 1 on OLED, right? So let's see what happens there. So I've left off the 1. Let me go ahead and again, let's do a make make exe1 synth. Let's synthesize this. And now let me program it. Oh, well, error loading PCF failed, right? But it didn't actually do anything else. I mean, it did say right here, error IO OLED is unconstrained in PCF. So basically it's saying, I don't know what this is. I don't see this in my pin constraint file. So go back. Let's change that to OLED 1, actually just for sample purposes so you know that this is working as we expect. I'm going to do OLED 3, change this to OLED 3 as well. We'll make it go high. And let's run this again. And what we expect is LED 3, hopefully here in a second, to turn on. And it does. So, okay. Another thing you can do, you'll notice that as you start doing work in these directories, lots of things are being generated, right? All these output files. So if I do a ls on example2 directory, and the starter directory specifically, you'll see that there's a lot of things. There's this binary, there's this dump file, there's the simulator, there's a lot of things. So super convenient. You can also clean things up. So you can do, hopefully this works. And if not, we'll show you how this can work. If you do a clean, oh, there's no clean. So to clean things up, a little bit more work, you can change directory directly into ext2. You'll notice that there's a make file within the starter directory. So clear this. So inside of the starter directory, here are all these files, all these things that I don't want, and there's a make file in here, which actually is getting used for a lot of other things. We can do a make clean, and it will remove JSON files. It will remove all of these additional files, and we're now left very cleanly with just our Verilog, which is all that we really need to do things. So that's, I think, the big run through of how things work. And we will definitely see more as we continue on. But for now, you've seen the bulk of what we wanted here. So let's go back to our slides real quick. And hopefully you've seen again modules to ports to assignments in an end module. Now we saw a lot more than that, but I think it was very important. So biggest mistake we see up front is missing semicolon after your port declarations there. So you absolutely need that semicolon to close things off. Error messages probably won't get you to the right place for this one. It'll probably point you to the wrong line number entirely. Another big thing that will happen is depending the difference between what you put in your ports description and what you actually use does make a difference. So if you have an input that's one size and an output that's another, and you try to do an assignment like that, you will get just silent truncation of information. So we will see that more over the next couple lectures, the next couple videos, but that is a pretty common mistake, is a mismatch between input and output sizes. So we'll cover this a lot more on day 2 material. I already showed you this example on the button logic. So one of the things that you'll have to do though for the actual lab is to start using some, I'll say some logic gates. And again, we'll talk more about those logic gates. But if we go back real quick, let's actually see how you can follow along and do that. So if we take a look here at our editor, what you're going to notice, so let me get this back to a state which makes sense here. So if we go and let me close all these, just start from scratch or a fresh space for you. So example 2 button LEDs, right? I believe that's the one. Actually, probably button logic here. So if we go to button logic and we open up button logic and we try to run, let's make 3. Make example 3 sim. See if that works. Oh, look at that. Some tests failed on it. It's because if we look, there's some to-dos for you in here for the lab. Okay. Notice right now everything is assigned to be 0, right? So if I were to make prog on this, we expect all the LEDs to remain off. So let me show you the overhead. All the LEDs are off. Buttons don't do anything. So that's pretty much the case here. But what we want to do is we actually want to embed some logic here. And so it tells us what we want. Basically, um, we can look here and say LED 2 on when either switch 3 or switch 4 is pressed. Well, so for this one, I switch well, autocomplete is doing great, but 3 or I switch 4. So I think let's just do that one. Let's just save that and let's rerun the sim. If for whatever reason you get kicked out of one of these, you've got to restart your prompt here, but it's okay. You're gonna go and you're gonna switch to the lab, the week that we're on, and this is example 3. Actually, we could just stay at the top level here. We can do make ex3. Let's do sim. Still says some tests failed, but let's open it up and actually for demo purposes, let's just program and see if this works. I'll show you live. All right, so it says that if 3 or 4 is pressed, we should see LED 2 show up. So let's see if that's the case. All right, that actually does work. And the other ones don't do it. They do, and both of them should also do it. Okay, so that was a quick sample here to show you that you can build in logic between your inputs. Okay, so going back to our presentation real quick. That was a really quick live demo, but you get the idea of what we can do. And so you can do all of these. You can do a direct connect, you can do NOT and an XOR, and we'll definitely have you do that for the labs. So question that you might ask is, hey, what happens if I declare a signal as an output register and then drive it with an assign statement outside of the module? Can I do that? And then, so what do you think will happen? So you might come up with a prediction. Maybe it'll have a compile error. Maybe there'll be a silent bug. What will actually happen? So good LLM will probably tell you, well, the external assignment to an output register is an error, and it should be caught by error Verilog. But you should try it. Compile, see what happens. And then a key here is using iVerilog, using the all flag, right? So that you see everything. So you see all warnings. Okay, big takeaways. Modules are fundamental building blocks, right? We have to define inputs, outputs, and the behavior between them. Assignments are permanent wires. They are not this one-time computation or assignment. They are physical wires that you are placing and connecting between components. Use ANSI port style naming conventions. Also use consistent naming for your inputs, outputs, registers, and wires. You will thank yourself later. Don't forget the semicolon after the closing port list. And with that, we're going to take a brief segue, brief refresher into digital logic for our next video segment. It is really a high-level refresher. Highly recommend that if this is something you haven't seen in a while or it's brand new to you, that you spend some additional time. But with that, until next time, thank you.